Streaming live via the internet, welcome to ISP Radio, your weekly source for ISP-related news, events, and interviews with industry experts. If you deliver internet via fiber optic, fixed wireless, coax, or any other way, you're in the right place. And now a brief word from our sponsors. Link Technologies Incorporated provides the lowest priced Microtech products in North America, as well as Wade Towers, Mimosa, Cambium, Ubiquity, Nettonics, and a host of other products and services to be your one-stop shop for your ISP needs. Visit www.linktechs.net. That's LINKTECHS.net for more information. TowerCoverage.com, providing online RF coverage maps with website integration. Stop rolling your trucks for every site survey and start doing installations. Visit www.towercoverage.com now. And now we'd like to present our hosts, Steve Grabiel and Dennis Burgess.
Welcome to another edition of ISP Radio. I'm your host, Steve Grabiel, broadcasting from my office here in Moriarty, New Mexico, where it's been a beautiful week. Just quite a bit of wind, but by and large, just real nice. I've been having to put on sunscreen every day as I'm out in the field plowing in fiber or installing new wireless customers. Things have been really taking off for us here. Look forward to additional growth with our added 10 gig pipe we're putting in, as well as modernizing our network to IPv6 with the help of Dennis. Just beautiful weather out here. Look forward to getting out after the show and to doing some work. So Dennis, what's going on in your neck of the woods?
Oh, I'll tell you what, we've been really busy this week. Just got back from a show in Canada, and I had a really good time up there. Just trying to catch up and get all the customers taken care of as normal. I did have some news to share with everybody, and this is basically going back, it was basically the past week. We had a urgent security advisory from Microtech, and I'm actually going to put this up on the screen here. There we go. And this advisory basically said that there was a botnet that was scanning random public IPs to find open WinBox, which is 8291, and www ports to exploit a vulnerability in RouterOS www server. Now, this was patched March of 2017. So if you have not upgraded your router boards since March of 2017, or you are on a version that is older than 6.38.5, then you could be hacked and you can get this exploit actually occurring. Now, I will sit there and tell you this is that typically, in my case, we typically block or turn off or disable the www service. 99.999% of the time we don't need it, so we simply block it. We simply turn it off. Furthermore, the 8291 we typically block to only very specific IPs, and this is done in our IP-based firewall, etc. So typically, most of our customers, if you are our customer and we've reviewed your firewall, then most of the time that should be safe. However, it is always still advantageous to upgrade to at least 638.5 or newer. Pretty much if you're on version 6, then you get a free upgrade. Very simple. You just click the upgrade button and it will work. This is a security advisory. If you upgrade to 638.5 or newer, it will remove any of the bad files, stop the infection from coming from your router or going out from your router, and prevent anything similar in the future. So with that said, you do need to upgrade your routers to 638.5 or newer. We have quite a few production systems on the latest, not the release candidate, but the bug fix version. So I would highly recommend everybody do that if you have not done so. However, keep in mind that if you do have your security up to date, then you should be good, but you do want to schedule a time to reboot that router and get it up to date.
All right, well, if that's it, let's get into the show. Today we have on the show again Preseem. We've got Dan Simon. He's the Vice President of Product Management, and Scott Loach, he's the Chief Technical Officer. Are you guys there?
Yeah, we're here. Yep.
Well, today's topic is on quality of experience, a new topic that I heard at last WISPapalooza, and I wanted to find out all about it. So, guys, let her rip.
Great. Yeah, thanks, guys. Thanks for giving us the opportunity to come on the show again. So when we did this last fall, we talked a little bit about monitoring, QoE monitoring versus network monitoring, and that was a little bit more about kind of what Preseem is and what we're trying to do there. This session is basically, I'll call it a network geek out. We're going to talk a little bit about queues, why queues are necessary in packet networks, how that translates into latency, how to mitigate that problem, and then we're going to do a bit of a deep dive into Netflix and what it actually looks like on the network. And I think for people who haven't opened up a bunch of Netflix flows in Wireshark or something, you might be surprised to see how Netflix actually behaves on the network. It's not what most people expect. So that's kind of, agenda-wise. I'm going to talk a bit about the packet queuing, the latency side, and then I'm going to pass it over to Scott to talk about the Netflix stuff, and we'll kind of tie the two together, and then hopefully we have time for questions and stuff after that. So as I said, this is going to be a little bit of a network geek out, so hopefully everyone's able to learn something, and we can have some fun discussion afterwards. So I'm sure everyone's had the experience of doing a big download or a big upload on their home network or even in the office or anywhere, and seeing that latency goes up and seeing that your web browsing gets super slow because of that. This is something that I think most people assume is just fundamental to the internet, right? Like this is just how the internet works. When a connection's busy, the latency goes up. But that's actually not true. And the reason that all of that happens is because of poor buffer management. And I'm going to basically talk about that whole situation, how it happens, and again, how it can be mitigated. But I mean, if you take one thing away from this portion of the presentation anyway, take away that the idea that latency goes up when a network is busy is just fundamental. That's just fundamentally not true. So let's start at the very basics, and we'll kind of go up a little bit higher or a little bit more as we go. So we've got a couple of diagrams here. So if you think on the left-hand side of a link, so this is just an abstract concept of a link, like reading bits out of memory, writing it out to the fiber or the copper, right? So just writing bits out as it goes. While it's writing an individual packet, if there's no buffering, then the NIC would have no choice but to just throw that packet away, right? So there's no place to put it as it's writing it out. The end result of that would be that you would have very poor link utilization. So you think if you're transmitting a packet, one comes in and you toss it, well, 10 milliseconds later or 1 millisecond later, a nanosecond later, the link might become idle because you're done transmitting and now you've got nothing to do. So buffers are incredibly important this is on individual port basis, are incredibly important to achieving good link utilization in any packet-based network. And of course, the general concept of packet buffers is how this is dealt with. The other thing that packet buffers do, kind of not directly related to the rest of the presentation, is it enables you to have multiple links fan into one link. If you were just going, if you didn't have that, you would have basically this problem of having to throw away packets be drastically higher, and it just wouldn't be possible. So again, packet buffers, packet queues, absolutely required in every network device. The devil's really in the details of how they're handled. So let's talk a little bit about queues and packet buffers and what that means. So I'm going to use the term packet buffers and queues probably interchangeably. It means the same thing. Let's take a really simple example here. So let's say we have a link that's 1 megabits per second, and we have 1,500 byte packets, so standard Ethernet packets, right? If you do the math on that, it takes 1.2 milliseconds to write that packet to the wire. So that's just the operation of reading a bit, writing a bit, out to the wire side. And in this little figure, we've got 7 different packets queued up in that link. And if each one of those takes 1.2 milliseconds, that means that packet at the top, the one that was queued last, the red one, is going to take 8.4 milliseconds to be transmitted. Okay? So this is really where the bulk of delay in your network comes from. There's really two types of delay in a network, right? You have propagation delay, which is just simply how long does it take the photons or the electrons to move across the link. And then you have queuing delay, which is essentially what I'm talking about here. This is where the bulk of it comes from. So all of this, the high latency under load is all fundamentally because of these queues backing up packets like this. So you might think this isn't such a big deal, but the problem is many devices, especially commodity hardware, has very high or very deep queues. So up until recently, Linux had 1,000 packet queue on every link, even if it was 10 megabit, 100 megabit, a gigabit. In this particular example, 1,000 packet queue would mean that you had 12 seconds of latency. So if you've ever done a ping and you've seen seconds, that's when you have craziness like this with very deep queues and packets waiting to be transmitted. The other place that kind of drives some of this is there's been a general rule of thumb for people designing routers that you need about 200 milliseconds of buffering on every port. So what that means is for a 10 gig link, you're going to have 10 times as much buffering as a 1 gig link, for example, and down the link rates. But it does amount to pretty significantly deep buffers on many ports. And when you get to commodity gear, where it's easy just to put in a RAM chip, like in a home router or something like that, and people don't really think it through, you can have very deep queues, and it just wasn't really considered at all what the impact of that would be. So if you think about this little queue I've got again, think about the red packet as being a DNS packet. So you're downloading something, that's the blue packets. You open up your web browser, you type in google.com, your DNS request goes up, and it comes back down, just simple one packet each way, and on the way down, it gets stuck in behind this queue. So 8.4 milliseconds, well, that's not so bad, but it could be tens or hundreds of milliseconds, and this can happen on every hop along the path. So again, significantly, latency in networks and latency under load is just strictly a function of having deep queues and queues that just aren't managed properly. If you've heard the discussion of buffer bloat, that's what this is about. So if you Google buffer bloat, you'll find all kinds of great articles. Not all of them are crazy mathy. Some of them are really nice reads, and you can get a good understanding of kind of how this all figures together. Where this gets a little complicated is the interaction with TCP. So again, the buffer bloat stuff talks a lot about this, but I'll try to summarize this in one slide, but it's kind of a complicated phenomenon. But as a quick reminder of how TCP works, there's no way in a packet network to know the actual bandwidth on the path, at least not in today's packet networks anyway. So there's no way to say, well, how much bandwidth do I have between point A and point B? So instead, TCP tries to learn that. It learns that by blasting out a bunch of packets into the network. If they all get acknowledged, it says, hey, the network's not busy, and it sends more next time. And you repeat that process forever until you get a loss. And the loss, basically, TCP says, okay, I got a packet loss. That means the network's full. I'm going to slow down a little bit now. And the end result is you get something like this little chart on the left. You get that increase of bandwidth and then a drop, an increase of bandwidth and a drop. This is the TCP sawtooth that many of you will have seen in Wireshark, for example. The real problem with deep queues is that when you have a lot of packet buffering, that loss signal gets delayed. It takes longer to get back to the sender because it's at the end of the queue. If we kind of jump back to the previous case, that first one, that 8.4 milliseconds, if we were to throw away that last one, that's an additional 8.4 milliseconds before the loss event gets back to the sender and it can react to it. And I've got another example of that on the right-hand side there, showing a heavier flow, again, the blue session there, and then some interspersed, we'll call it like interactive traffic, like DNS. So what happens here is the TCP congestion control algorithm, it finds a happy point, the rough bandwidth that's available on the link, but it can find a point where it's inputting network or packets into the queue at the same rate they're coming out, but yet the queue still has a lot of packets in it. So the packet queue is actually never emptying, and then you get this phenomenon of the latency that I talked about. This is called a standing queue. This kind of problem actually is happening in every one of your networks every second, always. This is a very common thing. And again, these deep queues are causing, even in this case, we take that orange one to be like a DNS request. A single TCP flow that's established this kind of standing queue is adding delay to every DNS request, every other TCP flow, for example. And again, this phenomenon happens for every TCP flow, not every subscriber. So it's actually even kind of worse. So simple example here, we've got that orange packet stuck in behind the standing queue for the other ones. So this is a really kind of, this part is probably the one part of buffer bloat that's complicated. There's some interesting math and analysis of congestion control algorithms and stuff that shows that all this happens. Really fascinating stuff, but in general, I guess I'm going to take it on faith that it does happen, and it is actually a very significant problem. So buffer management. So we talked earlier on that if you have too little buffer, you have very poor link utilization. In the last slide, we talked about if you have too much buffer, you have way too much latency. So this really makes buffer management kind of a Goldilocks problem, right? You can't have too much, you can't have to have too little, you have to figure out exactly what the right amount is. And this is where the whole space in network management or network science, I guess, around AQM or active queue management comes into things. So this is a very kind of rich area. There's lots of papers. I'm just going to summarize a couple of little examples here to kind of give you a sense of what AQM techniques can look like. But at a 50,000 foot view, AQM is really just about, let's not have a dumb buffer, let's manage it properly to achieve the high throughput without adding the high latency. So the simplest example is the approach we've talked about so far, which is tail drop. So this is the common thing that most access points and routers are going to implement, which is you have a queue, a packet comes in, if the queue is full, you throw it away. So this is the worst possible buffer management strategy, because again, it means that lost signal is delayed and TCP can't react fast, and you get a full queue and you get high latency and all that stuff. But unfortunately, it's the dumbest one with the worst possible customer experience, but it's also the easiest to implement, so it's pretty much what's implemented everywhere. The second example is head drop. This is it has much better performance characteristics, but it's a little counterintuitive, because intuitively you might think, well, I've already had this packet in the queue, why do I want to drop it after I'd already held onto it for a while, which is essentially what it means. At link time, you make it, or sorry, as you're in queuing a packet, if you need to drop something, you take it off the front, the back. And again, it's a little counterintuitive, but when you work that in with the dynamics of the TCP congestion control, it actually makes a huge difference, because it means you're able to get that lost signal back faster. Another technique you might have heard of is random early drop, or RED. Some routers, Cisco's, probably Microtek's, a few others, actually have an option to enable this on interfaces. This hasn't really ever taken off because it requires a bunch of tweaking depending on the traffic characteristics, which has been a huge problem. But came out in 1993, and essentially what it does is it says it kind of establishes a target offering, and if you exceed that, it just randomly drops a packet from the queue. And the idea here is that statistically, you're eventually going to whack a packet for the heavy user or the heavy flow, and then if things are going to level out, and you're going to drain the queue. So that's the really high level view of that. But again, the big downside has been that the RED technique requires tweaking in every network, which effectively means it really hasn't been deployed anywhere. And then in 2012, this algorithm called Caudal came out from Van Jacobson and Kathy Nichols, which are names you might recognize from a whole bunch of other interesting network research. And what this does is basically when you enqueue a packet into the queue, you take a timestamp. And at the end, when it's time to dequeue, you make a decision based on a target threshold as to whether you should drop the packet or not. So if you're over the target threshold, you drop the packet on the floor. If you're under the target threshold, you transmit it. And what this is trying to get at is establishing the difference between good queue, which is queue necessary to keep the link busy, and bad queue, which is adding latency. And it really floats around that target value to kind of keep that optimal amount of buffering in the queue. So this is, I think, a reasonably fundamental advance in queue management that happened a couple of years ago, and is slowly kind of making its way into products across the networking industry. But as I mentioned earlier, you also have the problem of packets being stuck behind a single queue. So after Caudal came out, a bunch of people got together and came up with this concept of FQ Caudal. And this has been recently standardized by the IETF as RFC 8920. I think there was 6 or 7 drafts that led to that. And essentially what FQ Caudal does is this really cool thing where you have a whole bunch of queues, and in our context, we'll talk about a queue or a FQ Caudal instance per subscriber. You have a whole bunch of queues, and each flow, TCP, UDP, etc., is essentially put into one of those virtual queues. In this example here, I've got 6 in the picture. We deploy 4,096 deploy with our customers. And flows are automatically categorized into these different groups, different queues based on whether they're bulk flows or indirect. So what this does is this provides some flow isolation, so no single flow can cause poor experience from other flows. And it also distinguishes interactive and not interactive. So again, if you're doing a big download, you don't really care if that one of those big download packets is delayed a millisecond while your DNS response comes back. That's actually really important to having a good quality of experience. And what's great about FQ Caudal is it gets rid of all the mess around having to guess what the proper application rates are, or babysitting a whole bunch of complex rule sets to determine what applications should be treated what way. And it basically just gets the right answer based on the behavior of the individual fields. This really drastically simplifies managing QoE and QoS on networks. So we've done this a bunch. I have a little customer anecdote there. A customer, WISP customer, who his buddy used his service and was always complaining that when his wife was watching HD Netflix, his gaming went to very high latency. After we were able to switch the plan enforcement to using FUCODL, then that all went basically all those interactive packets, they got their turn to transmit, and Netflix didn't have a chance to kind of take over the entire pipe.
So real quick here,
Yep.
before we keep going on, we do have a question, and I don't really think that this really matters too much, but I wanted to make sure I pointed it out. And the question comes into, if you have lots of bandwidth, is this a non-issue? And I don't really think that's really the case, because the amount of bandwidth is not necessarily the issue in this particular instance.
Yeah, so I guess there's two things there. So one, if you had infinite bandwidth, you wouldn't care. But very few places have infinite bandwidth, and it really comes down to where the bottleneck link is. So in any network path, you've got a bunch of links with capacity and one that's full. So that could be, in the WISP context, that could be the radio from the AP to the SM, or maybe it's a backhaul or something like that. Wherever you have congestion, you have a queue. And if you don't manage that queue in an intelligent way, bad things happen.
Yeah. Not a problem. I just wanted to make sure I asked that question before we got too carried away.
Yeah, no, that's great. Questions are good. So this type of thing really makes a big difference to the overall customer experience. And again, the biggest reason for that, I kind of alluded to earlier, is most ISPs enforce their plan rates. So by that, I mean a subscriber with a 10 meg plan only gets 10 meg per second, that kind of thing. They enforce it on the access point or the subscriber, the SM radio, or maybe an intermediate router or switch. But most of those devices implement just simple tail drop queues, which is just the worst thing you can do for a customer experience. So again, as I mentioned at the beginning, having high latency under load is not fundamental to the internet. It's really just a function of poor buffer management. So with that, I'm going to pass it over to Scott to talk a little bit about Netflix, and then we'll kind of wrap the two themes together at the end.
Okay, let's talk about Netflix. It should be fun. So why do we want to talk about Netflix? A couple of reasons. So number one, Netflix is by far the most popular application on the internet. About a third of traffic on a typical ISP network is Netflix. So maybe more or less on your network, but if you think about that, it's kind of crazy, right? 1 out of 3 bytes flowing through the network are Netflix. It's been immensely successful. And the second reason is because we have kind of a unique expertise in being able to talk about Netflix. Our previous product we worked on before, Preseem, for a couple of years was completely related to managing Netflix traffic on networks. So we have probably the most knowledge outside of Netflix on how this stuff works. And it's pretty interesting. So I've got a bit of a diagram here at a high level showing what happens when Netflix plays a video. And there's kind of 2 parts to this. There's what it does when it plays and what it does on the network. So when it plays a video, it says, okay, I need some video. I'm at second X of show Y. So I'm going to look at my buffer, and it's an internal buffer where it stores the video and audio segments. It's going to take the next one out of there, decode it, and put it on the screen. And what fills that buffer is the interesting part, and the part I want to focus on. So what happens on the network is when you press play in Netflix, you authenticate with their servers, and then your app goes out and says, give me the manifest file for this video. And the manifest file is basically a big list of different files encoded in different bit rates and different resolutions that your device that you're watching on can play. And it has 3 links, HTTPS links for each file. And those come from 3 different locations on the internet. So 3 different CDN nodes it shows you. And those CDN nodes are selected based on things like BGP distance. And then your app will select those nodes based on things like throughput that it can get from them, latency, and BGP distance to those. And your app will select, it'll establish several connections, so several TCP connections to different nodes, and then it'll get those file chunks using regular plain old HTTP over TLS. I've pasted an example of what one of these looks like. They're encrypted on the network, but basically it's a great big obfuscated string requesting part of a file, and it does it chunk by chunk. So it's not a big complete file download, it's chunk by chunk that it requests it. And basically what it's trying to do when it downloads files is keep the internal buffers full. So it has a big buffer. We'll talk more about that in the next slide. But if there's room in the buffer, it'll download the next chunk. If there's not room in the buffer, it won't download the next chunk. So this is a picture of some of the internal diagnostics of Netflix. And I'm going to talk about how this relates to playback, but you can try this at home. In any web browser, if you press Control-Alt-Shift-D, it'll bring up this diagnostic screen, and you can see what's going on. So you can see some of the things you can see here. It's using a large buffer, so about 125 megabytes of video is buffered in this example. That's about 5 minutes ahead of playback, so if something happens to the network, it's got plenty of buffer to keep playing through before it has to go fetch again. It's got the throughput at the bottom there, which is interesting. So this is Netflix's calculation of the network throughput based on the speed it's able to get when it downloads chunks from the network. And if it's unable to keep the buffer full, it'll switch to a lower bitrate video and it'll start a new buffer. And then sometime after that, the bitrate that it's actually playing will switch down to that lower rate and it'll be a slightly lower quality. And likewise, if the throughput is high enough that it can play a higher bit rate, so it's currently playing standard def and it thinks it has enough throughput to play high def, then same kind of thing. It'll start a new buffer, it'll start getting chunks from that high def file, and sometime later it'll switch up the video to that. And the details of actually how it does this, the details of that algorithm, they're proprietary to Netflix, and this is really the special secret sauce of Netflix's algorithms, because what Netflix is trying to do, they're trying to maximize the quality the user sees, so they're trying to keep that as close as they can to the available capacity of the network so that the user gets the most high def experience they can have, and they're trying to minimize the number of upshifts and downshifts, so you don't want the video sort of shifting up and down and changing, because that is visible to the user when that happens. And as a primary constraint, they're really trying not to starve that buffer. So no matter what, do not let the buffer empty, because that's when the dreaded buffering messages come up, and that's when users get really frustrated.
I got a quick question. Is that why doing bursting and selling bursting is just a marketing ploy? It really degrades the Netflix or streaming content, does it not?
Hey, that's a good question, because I was actually just about to talk about that. So one of the interesting results for WISPs with this is that a shaper configured with bursting can actually cause Netflix to misestimate the throughput when a video starts. So what's going to happen is if you've got a 5 meg plan and you're letting it burst to 6 megs for a little bit, then Netflix will detect, hey, I've got 6 megabits to work with. It'll start downloading something that may be above that 5 meg actual plan speed, and then you'll end up having some extra shifting up and down that you wouldn't have had otherwise. Now, it's not the end of the world. It's not that noticeable, so it's going to go lower quality, higher quality, and then when the burst ends, back down to lower quality. So it's something that may be noticed. It's a bit of a waste, and it's probably not going to cause it to actually stall. But yeah, it's not optimal. Okay, this is sort of a geek slide here. This is showing Wireshark, but I wanted one thing that kind of shows these different TCP connections, because it's important to understand that Netflix is this is not a real-time stream, right? This is the quote unquote not a stream that we're trying to get across. So if Netflix were a stream, when you think about, if I was playing a 5 megabit video stream, I would expect kind of a flattish line around the 5 megabit level, and that's what you would see if you were looking at this Skype flow, right? You'd see some video, it's being encoded. If I move around a lot, the bit rate's going to go up a lot. If I'm just a talking head, it's going to be a little bit lower, and it'll be stable around some, depending on the capability of my camera. If this is a 1080p camera, then maybe around 5 to 10 megabits. not at all what Netflix looks like, because Netflix is not really streaming. It's downloading chunks of files and trying to keep a buffer full. So that's what you can see on this. You can see at the beginning of the video there's a high usage while it fills that buffer initially for a while, and you can see that I've got the different flows colored there, so you can see it's actually concurrently using 3 different flows to maximize that throughput as much as it can. And then it goes idle for a little bit, and the video starts playing. And then after that, once the buffer starts to get some space in it, you see it's very spiky there. It'll go up and down as it tries to keep that buffer full, and it'll use those different TCP streams mostly at the same time, but it's using all 3 of them. And this is just one example using one device on one network. So it's important to understand that behavior may vary with different devices, with different network conditions, and also over time as Netflix does more research and changes their algorithms, because as I said before, this is something Netflix puts a lot of time and effort and research into. All right, next slide. Kind of a similar thing. So this is an example experiment I did. You can try this yourself. And I started a shaper at 3 megabits, started a Netflix show, and after a few minutes, I increased the shaper rate to 5 megabits. And in this case, Netflix did not choose a higher encoding. It didn't make that upshift decision, so it kept playing at a bit rate under 3 megabits. And I was trying to see what would happen if it was filling the buffer with video well below the available capacity of the network. And so you can see how it still uses all the available link capacity when it's fetching chunks of video. It's just not consistent, right? You see the buffer fills at the beginning, and then it plays for a little while, it gets some room in the buffer, goes up to 5 megabits while it fills it, goes down again, back up to 5 megabits, etc. So the point being that this is not, while it's filling that buffer for tens of seconds at a time, this is not leaving room for interactive traffic such as voice over IP, which kind of goes back to the problem Dan was explaining, where you may end up getting real-time traffic stalled behind those Netflix downloads. So that was sort of a deep dive into how Netflix works, and we can draw a few conclusions from this that I've listed here. So first, Netflix uses multiple TCP connections and it uses TLS. Therefore, it's not possible to limit the number of devices or the number of concurrent streaming sessions, even with DPI-based policies. You get a TCP connection, it's Netflix, but you can't tell which streaming session that TCP connection goes with. Secondly, Netflix videos are variable bitrate encoded. So kind of like I was saying about Skype, if there's a lot of action in a scene, it'll be a higher bitrate. If there's not so much action, it'll be lower bitrate. If you're watching an action film, it's going to be a high average bitrate for that. If you're watching a comedy show where it's just someone standing there talking, or a cartoon, it's going to be a lot lower bitrate. So a standard def video on Netflix actually varies from a few hundred kilobits to 3.5 megabits. There's that big of a range. So it's not really possible to limit resolution and just say, I'm limiting Netflix to standard def. There's no value you could pick that does that. And besides that, you don't know, as in the first point, when people are using more than one Netflix stream within their home. And then the last point, Netflix downloads in short bursts, as we've seen, at the full link rate, so that can negatively impact other traffic. VoIP, web page loading, gaming, you don't want those to be waiting behind a Netflix download. So a good strategy would be to use the capacity more intelligently, using a modern queue management technique such as the CODL algorithm that Dan was talking about. So the more capacity Netflix can use, the better the picture quality for the user. So you want to have the network that provides a great Netflix experience. You want to let Netflix use the capacity that it can, right? And the more capacity Netflix can use, the better it is for users. So you don't want to artificially limit that, but you want to make sure other applications won't be degraded by Netflix playback.
All right. So so I guess just to kind of to tie those two things together, the idea that Netflix is a stream is I guess it's very poorly named. It's not a stream. And those microbursts of filling the buffer really do have a big impact on any other traffic that's happening at that particular instant. And that happens even if they're watching a 1 meg stream on a 10 meg plan, but just because it tries to fill it as fast as it can in that short interval. And active queue management techniques, things like CODL, FQCODL, and other techniques as well, can really be used to mitigate that impact and give a better customer experience. So hopefully that was kind of interesting, maybe a little geeky, but if you have any questions, we'd be happy to answer them, and or you can send us emails. We're happy to talk in as much detail as anyone's willing to talk to us about for stuff like this.
Well, I've done this myself, throttling myself, watching Netflix. I throttled myself down to like 512, then it started to buffer, and then went up to 768, and it was fine, just standard def. I mean, I don't provide myself a big monster pipe at the house. But it seemed to flow okay at 768, but if I loaded it up with a couple of these streams, then it would definitely be impacted. But just testing it out myself, what does Preseem do to in the QoE? What do you guys offer us as WISPs as to help manage that buffer you're talking about?
Yeah, so what we do is essentially we leverage FQCODL and some stuff on top of that for each individual subscriber. So that earlier picture, I mean, this is a super simplified example, but this picture here of having those 4,096 virtual queues for every single subscriber, and what that picture is showing is that rate at the bottom is like their plan, right? So 1 meg, 10 meg, 20 meg, whatever that is. And within that, we give 4,000 virtual queues to every subscriber, and then the FQCODL algorithm actually does the work of determining that, well, Netflix is delivering a lot of packets, it's building a queue, therefore it's a bulk flow. I'm going to put the DNS lookups and short bursts of web traffic and stuff just right to the front of the queue. And that just kind of all falls out for free with this FQCODL algorithm. So from the QoE optimization standpoint, it's leveraging these advancements in AQM that allows us to deliver better QoE to the subscribers. And then there's a whole other part of what we do, which is the actual QoE measurement on tower, sectors, and subscribers. But that's not something we've really talked about today.
Right. I mean, to me, this makes a lot of sense, but I want my Netflix to flow better, and I want like you were talking in that slide about the child's gaming lagging because of the stream.
Yeah.
Does Preseem offer a box that we throw in our network that helps do this? Or
Yeah. So Preseem is deployed as there's two components. There's a cloud component where we have all the data analysis and QoE trending and all that kind of stuff. But in the network, we have an inline appliance. It can be deployed on a virtual machine, on your own server, or we have appliances you can buy as well if you need, bypass and that kind of stuff. And basically, the traffic just flows through. It acts like a transparent bridge, and we take all the QoE measurements, roll that up into the different dimensions like tower, sector, subscribers, and then can apply FQCODL and other optimizations on a per subscriber basis.
Gotcha. So we actually have a
ahead,
question
Dennis.
here. The question is where is the FQCODL implementation on a WISP network?
It can be abstractly, it can be in any place there's a queue in the network. If you're talking about Preseem, typically we're deployed where the kind of the highest point where there's no asymmetry. So if you have one individual transit link, we deploy right in front of that. If you have a couple, then you might take a smaller box. And again, we don't charge per box. We charge on a subscriber basis, so it doesn't really matter how many boxes you have. You could take a smaller box down to the tower or a portion of the network level. And what really matters is that Preseem ends up kind of owning the queue. So it's the spot where the bandwidth enforcement happens, and then everything below that does not do the enforcement, because what happens is even if you do smart enforcement at point A, if something farther down the line is doing dumb enforcement, for lack of a better term, you basically throw out all the advantages. So that's why it's important that when Preseem's deployed, that we're doing the entirety of the subscriber plan enforcement and the other devices aren't.
So like in my case, in some instances I have throttles and queues at the client's bridge. In this case, I would want to take that out and maybe deploy something like this at the tower and let the tower site throttle the customer to allow for these streams to get where they need to go and allow the other voice over IP traffic.
Yeah, exactly. Yeah. So if you have a like a managed voice thing on a different VLAN and stuff, that's kind of not exactly what we're talking about here. But yeah, that's exactly it. You take that enforcement out of that device that probably doesn't have particularly intelligent queuing, move it up to where we can do some smarter stuff.
Okay.
So let me ask this question. Couple very key elements here. One, are you functioning as the billing system's radius client that actually controls the bandwidth for each individual subscriber?
Yes, but not usually via radius. So we have integrations with many billing providers, VISP, Billmax, Sonar, PowerCode. I'm probably missing some. And we have custom integrations too with even just things like ISCP, DHCPD. But essentially, we just need to be told, hey, this IP belongs to subscriber A. Subscriber A has a download rate of 10 meg and upload rate of 5 meg, and then we do the rest.
Gotcha.
So it seamlessly integrates in with our billing systems.
Yeah, exactly. Yeah. So if I recall, you mentioned PowerCode when we talked back in October. I don't know if I remember that right, but yeah. In that case, we just turn on the PowerCode integration. It sucks out all the information on plans and what subscribers have what IPs. There's some SNMP stuff as well, so that we can map IPs to individual APs and stuff, and then away it goes. So there's very, very, very little configuration. That's been a goal of everything we've built.
So I have a couple more questions. So the IP address is being received by the client via DHCP, correct?
It depends on the network, but sure.
Okay.
Yep.
So, one, how do you handle IPv6 traffic?
Okay. So we don't have any customers with IPv6 deployed today. So that's something that we've done internally in our testing, but we don't have, of all the WISPs we work with, we have yet to find one that has it deployed in their network.
Gotcha. You probably have one later on today, but that's besides the point.
Okay.
Number two, let's just I'm going to use this as an example. I understand your box is specifically designed to integrate in bridge mode. Is that correct?
Yes. You can kind of think of it as like on each 2-port pair is like a 2-port switch.
Gotcha.
Yep.
And it can only function in that transparent fashion, correct?
Yeah, we don't have a router mode yet. That's something we've toyed around with and may do in the future, but that's not part of the product yet.
Okay. What about one peering into unencrypted PPOE packets to do bandwidth control?
Yep. Yeah, we have customers that do that.
Okay.
Yeah, so it's basically just a configuration to say, the subscriber traffic is inside PPOE or it's inside GRE or inside VLANs, and then we just kind of hop over those headers and get at the subscriber traffic.
Excellent. And what about VPLS tunnels?
Sorry, VPLS?
Yes.
Yeah, so that I'd have to do a little bit of research. We definitely have customers with MPLS. With multiple tags of MPLS. I'm not sure if there's something else with the VPLS that I'm
VPLS
not aware
is just
of.
another tag, so it's all unencrypted data. It's just a matter of it's an extra tag on top of the MPLS.
Okay, yeah. So if it's the standard MPLS tag format, it's not a problem. We just skip over them.
Gotcha. Alrighty. And with that said, I am looking to see if we have any other questions. Steve, you got anything else?
Yeah. Do you guys have any stories of dramatic improvements for the WISP community that have seen utilizing your Codel, your FQ Codel?
Yeah, so we have some testimonials on the website. If I try to do them from memory, I'm going to get them wrong. But that one, that we kind of have paraphrased on the FQ Codel site there, that's something we hear over and over again. I mean, we just had another one come in from another WISP yesterday saying the same thing, that the complaints of people getting slow internet when they were downloading and stuff just went away. So. If you'd like, I'm happy to reach out to any of us. We can get you some testimonials, but you can also find many of them on the website.
Right. Just, this to me seems like no-brainer. I don't know if you can talk about cost and like you said, you charge per subscriber. I mean, if we're interested in this and we contact you to just get our feet wet, what what's the cost involved in getting involved with you guys?
Yeah, so there's two components. So we do a 30-day trial on the hardware and the software. So you can choose to again deploy the Preseem on your own hardware, your own virtual machines, or you can choose to deploy it on our appliances, and we do a 30-day trial on that. And in either case, there's a 30-day trial on the software as well. In terms of pricing, we're pretty transparent on that. It's based on the number of subs. Starts at about 50 cents a sub. I think that's already been posted on the WISP or the WISP talk group, so I think not much point in hiding it now. And then depending on the size, there's discounts off that for depending on the total number of subscribers. But we don't charge per box. So if your network happens to have a topology that you need 4 little boxes instead of 1 big box, we really don't care. I mean, if you want to use your own hardware, that's perfectly fine to us. It doesn't matter.
So I'm looking at my network, roughly around 600 subscribers and growing. I'd be paying roughly about $300 a month for this benefit.
That's right.
Yeah, awesome.
So I have another question last on our chat. Do you support bandwidth limiting customers with multiple IPs? Very specifically, a customer has a 10 megabit plan, but they have multiple public IPs.
Yeah, so any subscriber or any IP is basically bound to a subscriber, and if they go through the same box, they will be grouped together under that subscriber's traffic envelope. So if you got 2 IPs and the subscriber's at 10 meg, then the 2 of them will be shaped at 10 meg together. If that's not what you want, then you can basically use the plan identifier along with the subscriber identifier so that you end up with a separate 10 meg for each IP. So it kind of depends on what the goal is there.
Gotcha. And if the Preseem appliance sits behind a power code BMU, how does that affect Preseem?
I guess it'll depend on whether the shaping's there. So if it's being used for counting, then that's perfectly fine. You know, feeding usage into power code. That's something that we'll be doing in the future as well, but we don't right now. But the important thing is that if the BMU or other devices are doing that management and they're not doing it in kind of the intelligent way that we're talking about, then that we're not going to be able to improve things as much as we'd like, I guess is the way to put it. So if there's a simple queue ahead of us that's full, doing optimization after it is just not going to have the effect that you'd like to see.
So I'm going to ask another question. So let's just say I have, it doesn't really matter what brand of access point, but let's just say I have a Microtech access point. I have 20 subs off of it of varying speeds. Does Preseem actually understand that those subs are, one, off of a particular access point, number one, and then number two, does it actually look at the overall capacity of that access point and make bandwidth adjustments as necessary to keep things to working as best as possible?
Yeah, so it does. So from reporting and metric side of things, of like rolling up and showing the QoE, that's done on a subscriber, sector, and tower level, and that's probably, in a lot of ways, even our main value prop over the optimization part is really understanding the QoE on each individual part of the network. But what we're going to be rolling out soon as well is the ability to put a bandwidth envelope on an individual sector. So you can say, yeah, this sector can never go above 30 meg, and within that, dole that out as fairly as possible in proportion to their link rates, all the subscribers that are on that link. So that's something that's going to come pretty soon.
So I guess my question, so the question is that currently does not figure out what that rate is and put that rate on it.
No, that's right. So when we do have the next release, you'll be able to say this particular sector gets 100 meg or whatever that number is, and then going forward after that, then there'll be some dynamic nature to actually helping you understand what that rate should be.
Gotcha. One question is the problem at the point. So a particular person said that they had a demo with you guys, and they said that Preseem only supported a 1 gigabit link. Is that still the case?
No. If you go to our website, we've got 10 gig appliances, and we have many customers deployed on 10 gig links.
Gotcha. And then where is this? And then how does it work with NAT?
Yes. So NAT's tricky. So we need to be south of the NAT. So we need to be in a situation where we can see an IP address per subscriber, and obviously that's because without that, there's no way to put the traffic for an individual subscriber into their own queues. So yeah, it's pretty fundamental that we're before any NAT in the network.
There you go.
Now, you may have already answered this, but I just want to ask it again, maybe. So I have a PowerCode BMU, and I just bought a 10 gig pipe, and I can't afford their 10 gig BMU, so I'm going to be using a MikroTik. Does the Preseem thing actually do the queuing itself, and it takes that load off of the BMU, or is it just analyzing the stuff coming out of the BMU?
Yes. So again, the two halves to Preseem. The one is the measure the QoE, understand it in the network. The other half is the optimization, which is the stuff we've been talking about today. So yes, we take over that role of enforcing the plan, and while doing that, doing the optimization with these AQM techniques versus just a simple queue. Yeah.
So in essence, I'm going to be going to the MikroTik with the 10 gig ports, and I was going to do a mirror from my BMU onto that. In this case, I wouldn't have to do that. I could just use a Preseem product.
Yes, you could use us for all the plan enforcement. What we don't do yet is feed usage to PowerCode if you have usage-based plans, but that's something that we're working with PowerCode and discussing with PowerCode about as well.
Oh, okay. But so if you, like most WISPs, were unlimited usage practically.
Yeah, so that it's no problem. Yeah, so we can absolutely take over the role of enforcing those plans. Basically, you just give us the credentials for your PowerCode server. Our software reaches in, starts sucking out all the subscriber information.
Ah, okay.
So then the other question, or not really a question, but statement that I have on that, Steve, is other than the usage information, which PowerCode does have in Radius. If you're using Radius, PPOE, i.e. I'm hinting towards that. But if you're using Radius with such as PPOE, then PowerCode can still get that data, and you do not even need a BMU.
Yeah. No.
It all works. All right.
Dan, you want to fire up that last contact page?
Yeah.
Oh yeah. Sorry. 1 sec.
Yeah.
And how far
So
back
you're going to
repeat some of the questions again?
Yeah. What was that? I'm sorry.
Are we just going to repeat some of the questions again, or what's the plan?
No. We got everything. Everything went out live. Apparently, we had a disconnect on our account here, and I'm going to get into our Creadio Studio. What's really great about YouTube, and I'm just going to sit there and say this right now, is that YouTube, we actually have the ability to restart a stream, which I know sits there, it sounds stupid. You would think in this day and age you would be able to restart a stream, but apparently not. So, at any which rate, we are still streaming. We did lose our stream here. I believe it was my workstation. I think I'm going to need to get me a new workstation. Darn your luck, right?
So Dan and Scott, we talked about Netflix pretty intensely.
Oh yeah.
What about the other streaming content providers? I've found that none of the others really have the algorithms that Netflix does. Like, I was behind a 50 by 50 megabit pipe in California, Verizon FiOS. We'd fire up an Amazon stream, and then my wife would fire up a game on her phone, and it just would buffer the heck out of it. Am I correct in saying these other content providers don't have the special sauce that Netflix does? They've got it down?
Yeah, I mean, Netflix definitely has the most money, and they definitely have the biggest R&D team, and they're doing the most research on solving this problem. All of the modern streaming providers will use adaptive streaming, so they all do some form of measuring the available bit rate and downshifting and upshifting based on what's there. But some of them won't be as good as adapting and as not having buffering events as Netflix.
They also have the advantage of having their massive Open Connect network that they've built out, which is their own special software. A lot of the other video providers, I think, end up going on a kind of a standard content delivery network.
Yeah.
So they don't have a lot of the tools that Netflix has available to them.
Does that mean bringing your Netflix servers closer to the end user if you've got enough bandwidth to justify it?
It's bringing them closer, and I think, and I actually don't, I mean, Scott can comment on this too, they also control the software stack on the other end, which I'm sure gives them a lot of benefits versus someone who just puts a video file up on Akamai, for example.
Yeah, they do. So they can control things like the size of the TCP buffers and things like that a standard CDN wouldn't let you control.
Right.
So I would be correct in telling my subscribers, yeah, Netflix has it down, but I have no control over what Netflix or any of these other people do, but Netflix by far has a more sounder network experience than your Amazon, your Hulu, your whatever. They've got it down, and you use these others at your own
peril.
Yes, exactly.
I mean, it's been a while since we've spent too much time looking at what Hulu and Amazon Prime do. But yeah, I think in general that's a pretty safe statement.
Would the Preseem product help with the Amazon content?
Oh yeah,
with the Hulu
because we're not application aware at all. Like the cool thing about all that FQCODL and those other AQM techniques is it just kind of does the right thing without having to know specifically what each individual application does. So if Amazon Prime, as an example, sends giant flows and is getting in the way of a game, well, having something like FQCODL, which isolates that from your web browsing and from your DNS, then they can be as bad as they want. They're not going to cause as much damage.
And that's the benefit of Preseem for sure. Okay, that's great. That alone adds additional value to your proposition.
Gotcha.
It's application agnostic.
Yeah, I mean, I wouldn't sit there and say that, Netflix, and that's just categorizing, but, I wouldn't sit there and say Netflix is the only person that does video analytics and does all that type of neat stuff. I do think that they are definitely ahead of the curve, if that makes sense.
Yeah.
Compared to many other providers. However, YouTube, especially since they started their live streaming, which we are doing now, which also successfully survived an interruption in stream. I actually see a ton of YouTube streams now. We have people, and this is horrible to say, but I know people that they don't sit there and watch movies anymore. What they do is they sit there on YouTube all day. And they may be streaming music, okay? And then they have 24/7 stations on YouTube now that has music and has dance and that type of stuff, all kinds of audio stuff and visualizations. That's all they stream. So I'm not going to sit there and state that that's not the case, but the end result here is that these guys can definitely give you that quality experience that people are wanting. I got one last question before we head out. I know we're kind of over our time here. How do you handle a NAT device such as LTE? In specifically, we have LTE base stations that basically only have NAT. So they NAT to one IP on our network. It's a public IP, but that's one IP, and we might have 30 customers behind that. How do you guys integrate, or do you have a preferred method to do that?
So the LTE base stations that I'm aware of, so base cells and Telrad that we see at most of our customers, those are not NAT only. Sometimes they're deployed in NAT mode. They can also be deployed in router mode or bridge mode, though, at least if you have the latest firmware. And as Dan was saying before, we can't do the kinds of analysis and enforcement we need to if we're behind a NAT. So if you're using base cells and it's an older version that only supports NAT, you just need to upgrade the firmware, use a router or bridge mode, and then we'll be able to see the IPs and manage them.
And we do have customers using both Telrad and BiCells.
Gotcha. So I just need to make sure there's no NAT.
Yeah.
Gotcha.
Well, you can have NAT, just north.
Yep.
Yeah, your product sits in north end of the NAT.
Yeah.
Wow. To me, it seems like this is intelligent or smart queuing. Outstanding product, guys.
Thank you.
Thanks.
Well, if anybody's interested in Preseem, there's www.preseem.com. Reach out to these guys. They'll be happy to help you out. I'll be looking into it for sure. But with that, Dennis, you want to wrap the show up?
Yep. Thank you, gentlemen, for being on the show. Sorry about our little interruption, but I'm sure all is well. We actually had quite a few listeners online, and I bet you'll have quite a few views afterwards as well.
Yep. Thank you guys for being on the show. We appreciate it.
Yeah, thanks for
Thank
the
you.
opportunity.